Assalamualaikum warahmatullahi wabarakatuh. The Honorable Daxmaners, Mr. Bayu, Mr. Pranawa, Mr. Farizi, and Mr. Rizal. Good morning. First of all, let me introduce my name Muhammad Daffa Afif Ramadan Tausa, NRP 0617040058, Design and Manufacture Engineering Study Program. I would like to thank for the opportunities that has given to me to present my final project with the title The Effect of Variation in Fiber Composition and Alkaline Treatment on Tensile Strength of Water Resin Fibers Reinforced Composite. Table of Content. Chapter 1, Background, Research Problem, Research Objective, Final Project Benefit, Research Delimitation. Chapter 2, Review of Related Literature. Chapter 3, Making Mold, Magnification Process, Density Test, FTER, Specimen Manufacturing, Tensile Test, Static Test. Chapter 4, Result and Discussion. Chapter 5, Conclusion and Suggestion. Chapter 1. Background. The background of my research, because Indonesia is one of the island countries that 2/3 of its territory is surrounded by ocean. So Indonesia has a lot of river. The river is a water resource and can also help the life of the community around the river. There are several plants that live in a river ecosystem, namely lotus, water hyacinth, water kale, watercress, and bamboo. Water hyacinth is one of the weed plant in the waters that live floating in the water. Water hyacinth has a very rapid breeding, so that this plant is considered as a plant that damages the environment. When the proliferation of water hyacinth cannot be controlled optimally, will appear a very detrimental negative impact on the ecosystem in the river, that is the lack of sunlight entering the water, so that it can lead to a decrease in the level of solubility of oxygen in the water. The swallowing of the river caused by the death of water hyacinth plant, and also difficult for fishermen who will go to work or go home after work. The level of water hyacinth is not yet comparable to the growth rate. If the water hyacinth is processed properly and correctly, will provide added value. An example of one of the utilization of water hyacinth as a composite manufacturing fiber. So far, the development of composite in Indonesia is still directed by a non-renewable material resource. Materials such as glass, carbon, amide. Therefore, it is necessary to natural fiber as a composite has many advantages. Such a fiber raw materials are easy to obtain and easy to update. For example, water hyacinth fiber composite material are very potential to see in terms of the availability of raw materials are very abundant, easy to obtain, low prices, and non-toxic. In the description, there is an idea to composite research with water hyacinth fiber and the manufacture of prototype response. Research problem. First, how is the analysis of variation in fiber composition to the mechanical properties of composite water hyacinth fibers? Second, how is analysis of variation in the concentration of alkaline treatment in the process of composite mechanical properties of water hyacinth fiber? Research objective. First, able to analyze the variation of fiber composition to mechanical properties of composite water hyacinth fiber. Second, able to analyze the variation of alkaline treatment concentration in the process of composite mechanical properties of water resin fibers. Final project benefits. First, can be a reference and information in the research of natural fiber from water resin. Second, provide general information about the utilization of natural fiber as a substitute for composite material from earth excavation. Third, utilizing abundant and untapped natural resources. Research limitation. 1. The type of water resin used is water resin from Kalimalang River, Kantong Village, Ilaga, Lamongan. 2. The liquefaction process using NaOH with concentration of 0% and 5% for 2 hours. Matrix 3. Matrix type used is epoxy. 4. Composite of fiber and matrix use 50% to 85%, 25% to 75%, 35% to 65%. 5. Composite manufacturing technique use a hand layup. 6. Mechanical testing performed is tensile test. For analyze fiber diameter is considered uniform by 0.5 mm. Chapter 2. Review of related literature. Composite. Composite is a material composed of 2 or more main materials where the properties of each material differ from each other in order to obtain better mechanical properties. Composite have better mechanical properties than metal, yang modulus or density and are higher in strength than metal. Composite are from 2 different types of material, namely reinforcement and matrix. Reinforcement serves as an amplifier or main that withstands load. Has less ductile properties, but it's more rigid and stronger. Reinforcement can use fiber and powders. Matrix is a composite material that acts as reinforcement binder, so that small strength of composite material depends on the strength of the forming matrix. This matrix has liquid properties with low viscosity, which will harden after the polymerization process. Lignification is a process and removal of lignin in fiber material so that the result of this process is in the form of cellulose with a concentrated puree. Water resin fiber. Water resin is one of the weed plants in the water that live floating in the water. Water resin has a very rapid breeding, both vegetatively and generatively. Water resin fiber as a composite material of natural fibers is very potential to see terms of the availability of raw materials as very abundant, easy to obtain, low price, and non-toxic. Tensile test. Tensile test is a method used a material to determine the ductility and toughness of a material by applying a force load of tensile stress to the material. Standard tensile testing refers to ISTM Chapter 3. Making mold. For specimen manufacturing, the main tools and material is laser cutting, acrylic, bolt and nut, binder clip. The lignification process. This process uses 0% and 5% NaOH solution for 2 hours. In this process, use a magnetic stirrer to help the immersion process. After 2 hours, the fiber is dried and prepared for the next process. Density test. The next process is density test. The initial stage of this process is to weigh the pignometer and fiber after the calculation using the basic formula mentioned in the basic theory. Then validate the decrease in lignin level with the FTER, tool and material, water reaction fiber, pignometer, digital scale, validated by FTER. FTER, Fourier transform infrared. The FTER test, the test specimen is a compound powder. The powder tested is fiber powder without immersion. 0% and 5% is a test using a tool to identify compound. The tool is spectrophotometer infrared. The analysis is done by looking at the result spectrum, where the specific peaks indicate the type of functional group of the compound. Specimen manufacturing. In specimen manufacturing, first calculate the volume fraction of fiber and resin. Then prepare a screen and fiber mold and then put the calculate fiber on the fiber mold. Then press the fiber, then leave the fiber mold. Then enter the fiber into the specimen mold and then the resin and catalyst that has been calculated in a ratio of 3:1. Then dry at room temperature. After drying, spare the specimen from the mold. Specimen ready for tensile test. Tensile test. Tensile test is carried out using universal testing machines Huangta instrument type HT2402. Capacity of machine is 10 kN and the standard of testing is ASTM D3039. Statistic test using ANOVA two-way hypothesis for composition of fiber. H0 variation in composition does not affect the tensile test result. H1 variation in composition affect the tensile test result. Hypothesis for alkaline treatment of fiber. H0 variation in alkaline treatment does not affect the tensile test result. H1 variation in alkaline treatment affect the tensile test result. H0 rejection condition. If p-value smaller than alpha equals 0.05, a value bigger than f double. Chapter 4. Result and discussion. Density test. These are some of the results from the density test. Including without immersion, the benchmark is 1.0H. Then after the lignification of 0% NaOH for 2 hours, it decreased to 0.53. And after the lignification of 5% NaOH for 2 hours, also decreased to 0.45. The decrease in fiber density is approximately 50% to 58% of the fiber density without the delignification process. FTER. Then here is the spectrum graph of the FTER test. The green line is the result of FTER from the fiber without immersion. The red line is the result of the 0% NaOH delignite fiber, and the blue line is the result of the 5% NaOH delignite fiber. In the 1800 until 1550 wave region, it shows C equals O stressing vibration and indicate the presence of lignin and hemicellulose. The peak indicators show a decrease in the NaOH sample of 0% and 5% of the sample without immersion. The decrease in lignin can be proven by the lower intensity of the wick on the peak sample of 0% NaOH and 5% of the sample without immersion. In this study, the C equals O bond was still present but showed a significant decrease in the peak intensity. So that a decrease in peak intensity indicate the delignification process could reduce lignin content but did not completely eliminate it. Tensile test. Next is the tensile test result on the fiber composition variable 15%, 25%, and 35%, and the alkali delignification variable NaOH 0% and NaOH 5% for 2 hours. At 0% NaOH delignification, the highest average tensile strength was at 50% composition. In the fiber composition of 25% and 35%, there is an addition of fibers, so when there are more fibers, the tensile strength will decrease. It can be seen in the following tensile test graph. This is because the addition of fiber composition will require more resin and the natural matrix of the fiber has not completely decreased due to the 0% NaOH delignification process, so that the bond between resin and fibers does not bind well. Meanwhile, at 5% NaOH delignification, the highest average tensile strength is also the same at 50% composition. The fiber composition of 25% and 35% also decrease, which can be seen in the following tensile test graph. However, the 5% NaOH delignification was more effective in influencing the tensile strength than the 0% NaOH delignification, and it can also be compared from the average of each composition, which has the highest average value, namely 5% NaOH delignification. This is because the natural matrix of the fiber has decreased significantly, so that the bond between resin and fiber can be said to bind well. ANOVA 2A. ANOVA 2A on the composition and delignification process, variable p value is smaller than alpha and f value is bigger than f double. According to the ANOVA result, there is a rejection of H0 in both independent variable. So it can be concluded that the composition and delignification affect the tensile tensile strength. Chapter 5. Conclusion and suggestion. Conclusion. Composition the highest tensile strength at 5% to 15% to 85%. Composition with the limitation in AOH 5% is 19.71 plus minus 4.60 MPa. Alkaline treatment, technification and OH 5% has the highest tensile strength. Suggestion. First, arrangement of fiber. In the future research, the arrangement of fiber can be done by using other methods of fiber placement, such as woven or continuous. This refers to the water resin fiber itself, which has a segmented stem structure and easy to shape. 2. Other tests, for example, bending, impact, or burn tests. 3. Micro observation. It is hoped that in the future research, micro observation such as SEM will be carried out. 4. Minimize voids. In the composition manufacturing process, the fiber and matrix mixture is carried out carefully or using the vacuum bag method to minimize voids. Reference. The following are some references from this research. The Honorable Examiners, I have presented all the content of my final project from chapter 1 until chapter 5. That's all about my presentation. I would like to apologize if there is a mistake, and thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.